Hi, welcome. Today's lesson is on the chain rule, which some people think is the dreaded part of the derivative. It's hopefully not as bad as they say, and we'll find out. First, we'll do a quick example showing the concept, go through the formulas, and some special cases. And then the most important part is doing it, examples. So first, here's a concept. What is x to the 7th to the 3rd? Well, that is x by powers of exponent to the 21st. And you should know what that derivative is. What is that derivative? You're right. It's 21x to the 20th. Okay, no, I didn't actually hear if you did it. But hopefully you know that one so well that that's not even a question. Now, how are we going to get this 21x to the 21x to the 20th in terms of the function in here in the power of 3? Well, x to the 7th derivative is 7x to the 6th, so we can maybe have that involved. What about taking something to the 3rd power? Well, if it were just something to the 3rd power, we'd bring a 3 down, and we'd kind of have to the 2nd. I'm not going to finish this one off because it's really not a complete derivative, it's just a concept. But how are we going to get that 21? Hopefully, you can see a way to get 21 is to take this times this. In fact, that will work if we want x to the 20th too, because x to the 20th is going to be x to the 6th here, and there are 14 left, which is 2 more powers of x to the 7th. All of this leads together to show us that we need this bit in there, and we need this bit in there, and they need to be multiplied. So that's what the derivative rule is. The chain rule says the derivative of f of g, when it's a composition like that, is f prime's derivative at g times g prime. There's this piece, and there's this piece, and they're both necessary. And it's important to remember, this one's easy to do, this one's easy to forget. You don't want to forget it, you want to multiply it on. Now, there are some cases that we've used in the past, like power rule and exponential rule, that we can now generalize to a chain case. So if I have something to the nth power, and I take the derivative, I pull the n down, just like that, and then it's the something to the n minus 1. But just in this case also, we're going to multiply by the derivative of the thing inside. It's n something to the n minus 1 times the derivative. Likewise for the exponential rule. Remember the derivative of e to the x is just e to the x. So the derivative of e to the something or e to the stuff is going to be e to the stuff, but then times the derivative of the stuff. We take the regular derivative of the outside times the derivative of the inside. Let's take some examples. Here are 3 examples. Try them out. I'll give you a couple seconds. Okay, hopefully you were able to pause and finish these. So how are we going to do this? This is the generalized power rule. It's something to the 8th power. So we're going to get 8 the something to the 7th. But we don't want to stop there because we have to multiply by the derivative of the thing inside, which hopefully you can tell is 2x plus 6. We could possibly stop there or we could combine. It's often good to combine things. Not always. Sometimes it's good to actually factor them. But if we're going to combine this 8 and this piece, they don't have any powers on them. They could just be multiplied. This is to the 7th, so we don't want to combine that in there. So if we were going to combine, we can take those together and get 16x plus 48 all times x squared plus 6x minus 1 to the 7th. And again, these two cannot multiply together, and that's about as much combination as you can get out of it. On the other hand, if you wanted to factor, we could have factored a power of 2 out of this. This I don't think factors in any useful way, but we could have pulled the 2 out, getting a 16 here, and left an x plus 3. That would have worked too if you prefer that. How about the second one? This is the generalized exponential rule. E to the something, we take the derivative as e to the something, times the derivative of that something. And that something is the cosine of x, and we know the derivative of the cosine of x, hopefully, is minus the sine of x. Now, aesthetically, we usually put the piece that's in the base in front of the exponential, but since the piece in front of the base is a function in its own right, we would still need parentheses, so it's not really any better. That's as much combination as we can make out of that. Hopefully it makes sense. This last one is messier. something to the third power. Hopefully you can see this is going to be the generalized power rule. We're going to get 3, that's something. Nothing else is done to it. It's just the same thing as before. That's a 2. It's a badly drawn 2. Minus 1 squared times, I'm not going to actually do it right away. I'm going to just write, this is times the derivative of the inside. Because that rule in itself is a little messy. Taking the derivative of this requires the quotient rule. If you remember the quotient rule, it's the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. And that's messy, so I'm going to write it out slowly. It's still 3 times this times, now it's the derivative of the top, which is 2x, times the bottom, minus the derivative of the bottom, which is also 2x, that's very convenient, times the top, all over the bottom squared. We don't stop there because when we have a quotient, these two pieces can have some simplifications, and we want to combine our powers nicely. So what do I have? 2x times x 2x cubed. I'm also going to have minus 2x cubed. They'll cancel. I have minus 2x from here and minus 2x from there. They don't cancel, they combine. So what do I have? I have 3, I'm going to write this as x squared plus 1 squared over x squared minus 1 squared. I'll talk about that in just a second. But the top was minus 4x, and the bottom was x squared minus 1 squared. So how did I do this? Well, when I take something squared and it's something as a fraction, it's the top squared, it's the bottom squared. So hence we have that. The reason I did this is because we have this squared, we have this squared. They can combine into more powers. And we'll end up, I'm going to bring this 3 in. When you bring a number into a fraction, it goes where? It goes on the top. So in the end, we're going to have the 3 times that is minus 12x. This is x squared plus 1 squared, and then we have an x squared minus 1 to the 4th. It's pretty messy, but hopefully it makes a fair amount of sense. Now if you have one to work on this way, I really suggest you do the steps slowly. So like this step, so then you can concentrate on the quotient rule after you've got it done. Or realize you're going to take the derivative of the quotient first, and then you can plug it in. Don't just try to do everything all at once, because that's the easiest way to get lost. Do it piece by piece by piece, and you get a better chance of success. Now that one's done, let's look at one more, finding a tangent line. Hopefully you can see this. I'll give you another 2 seconds. Hit the pause, start up again. And then, a special pause. The line tangent to here at x equals 1. How do we do that? A tangent line, you have to take the derivative. So the derivative here, this is a product. Now it's also a chain, which is outside, which is the first thing we do. Something times something. That's the outside. So the first thing we do is product. So it's the derivative of this times that plus the derivative of that times this. So the derivative of the first one times ex squared plus x cubed, excuse me, plus the derivative of the second one, which is e to the x cubed plus x times its derivative, which is 3x squared plus 1. And now you think, okay, I'm done. But no, that's just the derivative of the second one times the first one. It's messy. It's very messy. But we can use it because we don't know when x is 1. When x is 1, we get the slope of 2 times 1 times e to the 1 cubed plus 1 plus e to the 1 cubed plus 1, 3 times 1 squared plus 1 times 1 squared plus 1. It's very messy, but what are we going to get? 2e squared plus, that's an e squared, 3, 4 times 2, 8, 10. We get 10 e squared. That's our slope. So what do? We get y equals the number, which is 10e squared, x plus something. And when x is 1, we have 2e squared. So 2e squared equals 10e squared plus what? Hopefully you can see that's minus 8e squared. Finding a final answer of y equals 10e squared x minus 8e squared as our tangent line. Try it out. After you've done a few, hopefully you'll find that it's not as bad as you think. Until next time, this is Dr. Joe.